Introduction to matrices. So matrix algebra is very important in the real world because it helps us to reduce complicated systems of equations into simpler expressions. Our basic definition of a matrix states that a matrix is a set of group of numbers arranged in a rectangular or square array enclosed by two brackets. Here are a few examples of matrices. So this first example, we have a 1 by 2 matrix because we have one row and two columns. This next example is a matrix that we would say is 2 by 2 because we have two rows and two columns. And then our last example, we also have a 2 by 2 matrix. Even though we don't have actual numbers in the matrix, it's still an arrangement in a matrix form of two rows by two columns. All right, so we definitely have some matrix properties that we can look at. First, we want to look at the fact that each matrix has a specified number of rows and columns. It's never undefined. We know exactly how many rows and columns each matrix has. All right, so we have two numbers, again, rows by columns, that describe the dimensions of a matrix. So as in the last example where I was explaining what different types of matrix were, we can define every single matrix by its rows and columns. So again, here are some examples. We have a 3 by 3 matrix. Here we have 3 rows and 3 columns. Then we have a 2 by 4 matrix. In this next example, where we have 2 rows and 4 columns. Lastly, we can look at something like a 1 by 2 matrix where we have 1 row and 2 columns. All right, so we have a couple of special types of matrices. The first one that we'll talk about is a column matrix. And a column matrix is a matrix where the number of rows may be any integer. So I can have any number of rows, however, we only have one column. And so here's a few examples of column matrices. Next, we can have a row matrix where we can have any number of columns, but we only have one row. And so here are a few examples of row matrices. Next, we have what you call a square matrix. A square matrix is a matrix where the number of rows and the number of columns are equal. It doesn't really matter how many rows or how many columns as long as that number is equal. So here's an example. The first example is a 2 by 2 matrix. We have 2 rows and 2 columns, so we call this a square matrix. In the next example, we have 3 rows and 3 columns. This is also an example of a square matrix because we have the same amount of rows as we have columns. Again, it doesn't matter how many. I can have a 20 by 20 matrix as long as the number of rows equals the number of columns. It is said to be square. All right, so this next type of matrix is what we call the unit matrix or the identity matrix. We call it the unit or identity matrix because this matrix has ones along the main diagonal and zeros everywhere else. The size of the matrix doesn't necessarily matter, but again, we kind of want it to be a square matrix with the ones along the diagonal and then zeros everywhere else. So this first example is like a 4 by 4 identity matrix. Notice that it is also a square matrix with ones along the diagonal and zeros everywhere else. This next example is also an identity matrix or a unit matrix. Notice that it is still a square matrix with ones along the diagonal and zeros everywhere else. All right, and we also have what we call a null matrix or a zero matrix. And that's a matrix where we have zeros in every single entry. So every element of the matrix is 0. And so we can have like a 3 by 1 zero matrix, 3 rows, 1 column with zeros in the entire matrix. Or we can have something like a 3 by 3 zero matrix. We have 3 rows and 3 columns with zeros all the way through the matrix. Now let's go into some matrix operations. All right, so the first matrix operation that we want to look at is the equality of matrices. And so basically, two matrices are equal if all corresponding elements are equal. And so in order for that to work, that means that the two matrices also have to have the same dimension. And so if they have the same dimension and all elements are equal, we say that the matrices are equal or equivalent. And so, for example, I could have matrix A, that's 1, 0, 0, 2, 1, 0, 5, 2, 3. And then I could also have matrix B, which is 1, 0, 0, 2, 1, 0, 5, 2, 3. Looking at these two matrices, they're both 3 by 3 matrices, and every single element corresponds to the element in the other matrix. And so I would simply say that A equals B. All right, so some more matrix operations. We have some laws. So the first law that we want to look at is the commutative law. And the commutative law says that we can add matrices in any order. So if I want to add matrix A plus B, I can also add matrix B plus A and get an equivalent statement. So I can add in any order that I want to add. The next law we want to look at is the associative law. And that says, again, that I can add in any order, even if I have a third matrix. So I can do A plus B plus C, where I add B plus C first and then A. Or I can have A plus B plus C, where I add A and B first and then add C. Either way, I'm going to get the same solution. I'm going to get A plus B plus C, and it doesn't matter which one I added first. All right, so for example, if I wanted to add these two matrices, 7, 3, -1, 2, -5, 6, and I want to add that to 1, 5, 6, -4, -2, 3, I simply add the corresponding elements. So I'm going to add 7 and 1 to get 8, 3 and 5 to get 8, -1 and 6 to get 5, 2 and -4 to get -2, -5 and -2 to get -7, and then 6 and 3 to get 9. Now notice our original matrix A was a 2 by 3 matrix. Our B was also a 2 by 3 matrix, which allowed us to add them. Because in order to add two matrices, the dimensions must be the same. And if the dimensions are the same and you do add them, then your answer matrix, which we will call C, is also going to be the same dimensions of A and B. In this case, our answer C is a 2 by 3 matrix. All right, so a couple more properties. We have that a matrix A plus the 0 matrix equals 0 plus the A matrix. In other words, I can add that in any order. And either way that I add it, I'm just going to get the A matrix back out. I can also look at matrix subtraction and kind of think of it as addition, where I have A plus negative A is going to give me that 0 matrix. All right, so if I want to subtract two matrices, again, the easiest way to do this is to take each element and subtract them in order. So I'd have like 6 minus 1, which is 5, 4 minus 2, which is 2, 2 minus 0, which is 2, 3 minus 1, which is 2, 2 minus 0, which is 2, and then 7 minus 8, which is -1. All right, in addition to being able to add and subtract matrices, I can also multiply by a scalar. So a scalar, remember, is just a constant number like 5 or 2 or -7, and we can multiply that by a matrix. The easiest way to calculate this is just to multiply each element in the matrix by that constant or that scalar. All right, so for example, if I wanted to multiply the matrix 3, -1, 2, 1, 2, -3, 4, 1 by the scalar of 4, I can multiply that either in front of the matrix or behind the matrix. It really doesn't matter. And then when I multiply it again, I'm multiplying each element inside that matrix by my scalar, in this case of 4. So it's going to be like 3 times 4, -1 times 4, 2 times 4, 1 times 4, and so on. So my final answer for this would be 12, -4, 8, 4, 8, -12, 16, 4. All right, so a few more examples. Let's say I wanted to add the matrix -1, 2, 0, 1 to 1, 3, -1, 2. Because they're both 2 by 2 matrices, I can perform this operation. And so just remember that when you add two matrices, you add the corresponding elements. So I'm going to add -1 plus 1, I'm going to add 2 plus 3, 0 plus -1, and 1 plus 2. Now when I add those together and simplify my expressions, I'm going to end up with 0, 5, negative 1, 3. All right, so similar situation in part B. I'm trying to add a 3 by 1 matrix to another 3 by 1 matrix. Again, since those dimensions are the same, I can add them. So I have 1, negative 3, negative 2, plus negative 1, 3, 2. And I want to add those together to get 0, 0, 0. And so I see that my final answer is the 0 matrix. And not only that, it is a column matrix because it only has one column. So our final example for addition is we're trying to add A equals 2, 1, 0, 4, 0, negative 1 to B equals 0, 1, negative 1, 3. These two matrices have different dimensions. So A has dimensions 2, 3, and B has dimensions 2, 2. And so because the dimensions are different, the sum is undefined because I can't add two matrices of different dimensions. All right, so the next example, they're giving us a matrix A, and they want us to find 3 times A. So we're multiplying by a scalar of 3. And so remember, 3 times A, I could set the 3 in front, or I could set the 3 behind it. Doesn't really matter. But essentially what you want to do is multiply each element in A by that scalar of 3. So I'm going to do 3 times 2, 3 times 2, 3 times 4, and so on. And when I simplify that out, I get a final expression of 6, 6, 12, negative 9, 0, negative 3, 6, 3, 6. All right, so here's pretty much all of our properties of matrix addition and scalar multiplication, all in one total combined picture. And so we have the commutative property of matrix addition, which basically says that I can add two matrices in any order. I have the associative property of matrix addition, which basically says that if I have more than two matrices, I can again add in any order. It doesn't matter which two I add first. I have the associative property of scalar multiplication, which basically says that if I'm multiplying by 2 or more scalars, it doesn't matter what order I multiply those scalars. I can multiply the scalars first and then multiply it by the matrix, or I can multiply like one scalar by the matrix and then by the other scalar. The next one, we have the scalar identity, which says that if I multiply any matrix times 1, I'm going to get the original matrix back. I have the additive identity, which says if I add a 0 or a 0 matrix to any matrix, I'm going to get the original matrix back. Then I have the distributive property, which says if I'm multiplying by a scalar, I can either add the two matrices first and then multiply by the scalar, or I can distribute that scalar in and multiply it by each matrix and then add it. And then lastly, I have the distributive property. Again, just a little bit more in depth. If I have two scalars, I can add those two scalars first and then multiply by the matrix, or I can add each scalar to the matrix, or multiply each scalar to the matrix and then add the two matrices together. All right, so here's another example just to show kind of some of those properties that we saw on the last slide. And so basically, again, I can either add the two matrices first and then multiply by the scalar, or I can distribute the scalar into both matrices. In this example, I chose to multiply into each of the matrices. And so when I do that, I end up with negative 6, 0, 12, 3, plus 12, negative 6, 9, 21. Now I can add the two matrices together to get 6, negative 6, 21, 24.